I remembered that I had 3D printed models in my office. I did tell you that if you took that hyperbolic paraboloid and thought of it on a circle, you'd get a Pringles potato chip. So here is your hyperbolic paraboloid. I did decide, though, that I would actually like to see the hyperbolas. So I made another one and then proceeded to draw on it with a Sharpie. And you can see in one direction, I have a hyperbola that opens on one way, and these are on the top. So that's a section at a high Z, a Z that's positive. And then on the other side, they're going the other way. You can see through it. So depending on which way you set up the equations, you can either have the high ones go in the X direction or the high ones go in the Y direction. So that's our hyperbolic paraboloid. Yeah, it's actually printed in two pieces and then glued together down the middle. But instead of talking about surfaces, I want to talk instead about curves. We already did lines, but a line is still an example here. We're thinking of a vector valued function. So its output.
This is the same one.
Yes.
And this is on the.
Yep. Its output is a vector. Its input is a single number. So R of t is just a number, but we get out a vector in 3 dimensions. So I can think of R of t as 3 functions, x of t, y of t, z of t. Oh, those are our parametric ideas. So if we have a 3D setup as parametric equations, whether we do it in component form or IJK form, it's still the same idea. Like the line we were working with last week. That was Thursday last week. Only we didn't write it as one vector, we wrote it as separate vectors. I believe if you go back and look at your notes, we wrote this as 215 plus t times 1, 6 minus 7. A starting point and a direction vector, right? But these two are exactly equal. It's just whether we separate the t parts from the rest. And that describes a set of points in 3-dimensional space. In this case, it's a line. But as we saw in one of the homework questions from 12.4, where we had vectors that were in terms of t, we don't have to use simple, straightforward functions. I can use any function. Here's a different vector valued function. In the x direction, we go t cubed. In the y direction, we go 1 minus t squared. In the z direction, we go square root of t. Wait a second. I got to think all the way back to my algebra class. When we have a function, we have a domain. Well, now I have 3 functions. But I'm really thinking of it as one thing. It's not just x of t, y of t, z of t, it's r of t. And that one function should have a domain. So if I think of this as one function, I can ask the question, what is the domain of this function? Algebra was a long time ago, man. How do you find the domain of a function? All right, let me ask you a different question. What is the definition? What's the idea? What does a domain mean?
Values of function.
But I'm not using X here, I'm using T, right? So I want to know what T values are allowed in. So what T values are allowed in here? T cubed. Anything you want, minus infinity to infinity. Same thing here, right? But here, I can't use anything negative. Okay, so if each of these has their own domain, then the domain of the whole function is the intersection of the domains of each of the pieces. So we said that for T cubed, we could use minus infinity to infinity. For 1 minus T squared, we could do the same thing. But for square root of T, we could only use the positive numbers and 0. Well, when I intersect all three of those, I only get the positive numbers and 0. So non-negative real numbers are allowed in. I'm going to tweak this just a little. Here is a slightly modified function. What's the domain of this one? Well, since these two pieces didn't change, those two pieces don't change. It's just this one. So what numbers are allowed into a logarithm? Right, I can't use a negative argument. The thing inside can't be negative. But I've got 3 minus t inside. So to find the domain of this piece, I need 3 minus t be strictly bigger than 0. Because you can't take the ln of 0, that goes down towards, that's our asymptote, right? So I need that to be bigger. What set of t's does that? Be careful. If I move the 3 to the other side, I have minus t greater than minus 3. So t itself is less than 3. Oh, wait a minute. This one says I can't use any negatives. This one says I can't use anything bigger than 3. So my total domain goes from 0 to 3, but doesn't include 3 itself. Best part about these domain ideas is that they are exactly the same as the domains were in Calc 1 in algebra. I just have to do 3 of them instead of 1 of them. That's it. I said this to you at the beginning of the semester, that Calc 3 is Calc 1 with more letters. I just have to do the same thing 3 times instead of once. Questions? We did this with a line segment. We took the equation for the line and said, let t only go from 0 to 1. By restricting our domain, we took the whole line and just got a piece of it. So if I restrict my domain like this, instead of getting a giant set of, I may only get a finite piece of a curve. I may still get an infinite piece. I mean, I've got something that has an asymptote in it. So maybe this will have some sort of asymptote as well. Okay. I'm all the way back in Calc 1. We have functions. What was the first thing we did with a function in calculus terms? Chapter 2, a year ago, at least.
The lines, tangents, or code.
But before we could do lines and tangents, we had to do tangents, right? And tangents were, how do we find a tangent? It's not tangent then. It's perpendicular, it's not tangent. We can find perpendiculars too, but we're not until we do something mathematically. What did we do to find a tangent line? I'm sorry? Instantaneous rate, but the instantaneous rate of change is a derivative, and to do that instantaneous derivative, we needed, before we did derivatives, to get from average to instantaneous, we needed limits. Because the instantaneous rate of change is the limit of the average rate of change. The derivative is the limit of the, how do I do a limit in this? I just do 3 regular limits. Make it a instead of 0. Quite literally, taking the limit of a vector valued function is taking the limit of 3 individual regular functions. So here is where I think, again, I'm going to say this. I am just doing the same we did in Calc 1. Which means if I need L'Hopital's rule, I'll need to do it in the appropriate place. If I need to do a crazy looking piece of algebra to do my limit, I'll do it in the right place. Imagine that these are really 3 separate problems from Calc 1, and you're doing exactly the right thing. So literally, I know how to do that problem because I know how to do the limits of each of the component functions. As t approaches 4, what do I do with t cubed? Oh, come on, some of you were in my Calc 1 class. I know you should know this. Yeah, I pulled 4 out of thin air.
These about values.
Yeah, well, what do I get? When I do the limit as t approaches 4, I just plug in, right? Why? Why am I allowed to just plug in? I plug in here. 1 minus 4 squared is 1 minus 16. That's negative 15. 4, take the square root, I get 2. Why am I just allowed to plug in? I'm all the way back in chapter 2, trying to remember what the hell we did last September. Or maybe the September before. This is where I say, do you have your books with you? Can you look up the table of contents for the book and look at the table of contents for chapter 2? Fill in the blank. Continuous at 4. Hey, wait a minute. Okay. Search back in the brain cells and dig out the definition of what it means to be continuous. A function f is continuous at a point if there were 3 conditions on the first exam in Calc 1.
There's no jumps.
No jumps. No other things. Jumps. Sorry? I can repeat values. Cosine repeats values all over the place, doesn't it? So it's not repeating that way. Back, or okay, but that would make it not a function, right? Functions can't pass it. If it doesn't pass the vertical line test, it's not even a function. So I can write that one off right away. I said a function is continuous. No holes, no gaps, no asymptotes, all sorts of things, right? But when we did the definition, we did it by limits. We said we had to have a limit from both sides and they had to agree. So we have to have a limit at this point. We also have to have a value at the point, and the limit and the value have to match. So that were the 3 conditions for continuity. A function is continuous if we have a limit at the value in question. We have a value, a y value or an output at the value in question. And that limit and that value match. So I will say that R of t is continuous. US, I can spell really honest, is continuous at t equals a if and only if x of t, y of t, and z of t are all continuous at a. In other words, everything I already know about what makes something continuous stays the same. I just need to do it 3 times instead of once. Woohoo! If I want to do derivatives or integrals or tangents or any of that crap, I need to make sure that the basics underneath all that still work the same way. And if they don't work exactly the same, I need to know how they're different. So at the moment, I'm starting all the way back like it was day one of Calc 1. I have functions. I'm going to take limits. Now that I have limits, I'm going to look at continuity. Once I understand limits and continuity, I can figure out derivatives. But I got to start with limits and continuity. We figured out where things were not continuous by looking at places where we had jumps and holes, and looking at places where the domain was a problem. Where did we have asymptotes? So really, these two ideas about continuity and about domains are deeply intertwined, because that's exactly the sort of crap we had to look at last year. Questions? Well, in order for me to know what's going on, I need at the very least some way of making a picture. I'm a very visual person. I want to understand this in terms of graphs. Mia, you said average rate of change. I drew lines, right? And then I drew them on a graph. I'm going to take my 3D vector function, and I'm going to go to 2D vector functions. And a 2D vector function would be a regular graph on a piece of paper. It'd be parametric equations. So here, I'm going to make up an equation. I just pulled this out of thin air. Grab your graphing calculators. That's x of t and y of t. I can draw this picture, right? I can go into parametric mode and set x of t and y of t. And I can draw this. Let's do that. Mode. I got to change the mode to be parametric. Need actual paper so the white balance doesn't screw me up. Here we go. Mode, parametric. Then I go to y equals and I see x of t, y of t, 1 plus t, 2 plus 5t. Perfect. Now I'm going to change the window setting here. When I go to the window, the first thing it gives me is t value. By default, it assumes I'm doing something with trig. So it does 0 to 2 pi. I don't want to do that. I'm going to make my smallest t value -4, my biggest t value 4. And right now, the x and y parts are set to be fairly small. So I'm going to blow that back up to normal and go -10 to 10, -10 to 10 in both x and y. I didn't change the t step. That's the distance it jumps in t before it plots points. But you could if you wanted to. I just don't care at the moment. Hit graph. What before I hit graph, what should I see? Oh, wait a minute. That's a linear equation. I should see a line. Zoop. There we go. And not only is it a line, it's a line with slope 5. How do I know it's a line with slope 5? The t part. Change in 1, change in 5. Aha. So if I were to break this up and write it the way our other linear equations went, I could write this as 1, 2 plus t times 1, 5. So there's my slope and there's my point. I don't know what the intercept is, but I know it goes through the point 1, 2. And there's the point 1, 2 right there. but I've got a slope of 5 here. Technically, this line has a direction. As t is increasing, we are going this way, up and to the right. So if I were to graph this by hand, I'd put a little arrow on it indicating that direction, like we did last semester with our parametric equations, right? Okay. So I have the point 1, 2, I have a slope of 5. So if I back up 1, I should go down 5. I can draw this line with my half-assed ability to draw. With a straight edge. There. I suck at drawing. Take my word for it, that's supposed to go through that dot. What I don't see on this picture is the actual vector r. What I see here are the points I get for different values of t. So where is the vector r itself? R is in components, right? We wrote it in component form. And if I pick t equals 0, I should hit that dot. So r of 0 actually goes like that. It goes from the origin to a point on the curve. R of -1 goes here. How do I know that? Well, if I put in -1, I get 0 and -3. R of 1 is going to go somewhere up here, right? R of -2 is going to go somewhere down here. R of 1/2 is going to be somewhere in the middle here. So R of t is sweeping out this line from the origin. You can think of it as extending to different points. R of t is how we trace points on our curve. Yes? Believe it or not, older computer graphics systems used to use exactly this method, and they were called ray tracing monitors. One of my favorite video games was designed as a ray tracing game. It's called Tempest. Stand-up arcade cabinet called Tempest. You should look this game up. It is the weirdest trip you've ever seen. Tempest like a storm. Anyhow, that's for later. But ray tracing like this works in 2 dimensions. It works in 3 dimensions as well. If I write out an equation in 3 dimensions, well, then all I have to do is picture that vector tracing out the points in 3D. So here's a line. I know this is a line based on what we did last time. But what that means is that when I have t equals 0, r of 0 in this case is 1, 2, -1. That means we start at the origin and point at that spot. 1, 2, -1. So this spot is on my graph. And then I move as t goes on. I move in the direction 1, 5, 6. So I move forward and left and up. I have a line in three-dimensional space. And as t changes, I point at different spots on this line. And I don't care what the line is, I always think of myself as sweeping out this line exactly the way we did here, only I'm just doing it now in 3D instead of in 2D. And again, I'm a bad artist. But what happens if my equation isn't a line? What if it's something funky? This is not quite the problem that was in the homework for chapter 12, section 4, but it's very similar to it. So let me think about what's going on here. I'm going to think in 2D to start. So for the moment, let's ignore that. What's that graph as t gets bigger? Wait a minute, x equals cosine of t, y equals sine of t. I know that sucker. What picture does that make? Out come the graphing calculators, draw it again. What do you get? Not just any circle. I get the unit circle, right? Cosine and sine. This is where they come from in the unit circle. So I get this picture. But wait, there's more. What does that tell me? What does that t tell me? Wait a minute. If I put in t equals 0, I'm at the point 1, 0. And as t gets bigger, I go around this circle counterclockwise, right? So here I go again. I start out here and I draw the circle counterclockwise. I brought it for you. X-axis, y-axis, circle. Yes? X-axis, y-axis, circle. But this part, this extra t here on the end, says that as I go around the circle, my z value should do what? It should be bigger. So hold your hand out in front of you. Now, I'm going to spin. You can't, you're seated. But as you go around, bring your arm up. What do you see? You're drawing a spiral. There it is, spiraling around my tube. Aha! Again, I'm a crappy artist, so it was not really drawn very well, but there you go. As I go up, I go around. This is a helix. This graph looks like this from above, but from the front, it's going back and forth and back and forth like a cosine wave. From the side, it's going back and forth and back and forth like a sine wave. Which trace am I looking at? This is a helix in 3D. So I go round and around and around the circle, but at the same time, I'm also going up. And again, I will freely admit, I'm a bad artist, so here's one in the textbook on page 849. They've even drawn the cylinder, and they've drawn the helix going around it. And we picture different times, we have a vector that points at a spot on the helix, just like our arm was doing as we spun around. And I'd love to tell you it's worthless, but there's my favorite helix. Actually, I'm going to take that back. That's technically my second favorite helix, because my first one, I made. I made my wife crazy. She made this hat for her stepfather, but the pattern makes the hat with ridges that go straight up. And the way you make the pattern go straight up is you make the circle 100 stitches, and then you put a bump every fourth stitch, which means the bumps line up. And I said, so if I put an extra stitch in and I make it 101, the bumps won't line up each time, right? And she said, I don't know. And I said, well, then I'm going to do it. My next goal, by the way, is to make one where the bumps go the other way. So then I have the double helix, just one in each half. But it doesn't matter what the curve is. By the way, what was the one in the homework? Chapter 12, section 4. If I flip back to that problem, we had find the cross product. What was the equations there? Oh, it was T cosine sine, right? Ti cosine. So we reversed the order of those things, yes? So in that problem, the first component was the T. What's that do to my helix? Instead of going up the z-axis, it goes out the x-axis, around and around in y and z. Remember, we said if we rearranged pieces, we could always make the symmetry with our quadratic surfaces, the paraboloid and the ellipsoid, the hyperboloid, we could always make the symmetry up and down. Here's a way of rearranging to point it in another direction. Hot damn. The other one in that problem was 1 minus sine t plus cosine t. 1 minus sine t cosine t. All right, wait a second. If x is 1, that's not changing, right? That means this doesn't go back and forth along the x-axis. It just stays at x equals 1 and goes around in the circle. But minus sine t cosine t, I'm not sure if that goes clockwise or counterclockwise. We'd actually have to check. But again, I have a circle, only instead of a helix, it's a flat circle in 2 dimensions. So I can picture the vector function spinning around in the plane x equals 1 in front of me. Questions?
Or back to the point, the different changes in the city.
Yeah, as t changes, I move across this curve. Again, I'm going to stick with people who are better artists than me. My vector r of t always points from the origin to some spot on my curve. No matter what that curve looks like, r of t is pointed at it. As t changes, I'm following that curve.
So why do you make the vector the point?
Well, because that's what this point describes, right? The vector tells me where to go. The curve itself follows the tip of my finger. So this is, let's go really late at night. and we'll take our camera and your phone or your phone, and we'll record a video, right? And I'm going to take a glow stick and I'm going to write in the air. But you won't see me if you do a long exposure. You'll just see the glow stick, right? But my arm was pointing at these spots and the glow stick is tracing them through the air. Yes? Right. I can't make the curve without describing it somehow. And the easiest description in 3 dimensions, say, go there. Now move like this. Again, I will freely admit, I'm a bad artist. So the way in which we draw these matters, and that's important. So here, I'm going to try and draw a picture. I'm going to draw a pretzel knot. It's called a trefoil knot. And you start with a pretzel. See, if I take away this piece, isn't that a pretzel? You just finished out the loop. Now, the problem is that's just looking at it flat. It should be 3D. So I need to know which of these crossings here go over and which ones go under. So I'm going to draw this one. See which ones go over and which ones go under? By drawing which one is solid, which one is dashed, I can determine over from under, right? This, the way I've drawn it, the J in the bottom is on the right. But I could just as easily draw it another way. I could draw the reverse of that. That's a mirror image, right? I've got one that's right-handed and one that's left-handed. Here's the interesting part. In 3D, you cannot switch from one to the other. These are chiral molecules. They're handed. You have to take it apart and put it back together to switch sides. They're 2 different versions of the same picture. So I made one. This is the same knot. Loop, loop, loop. It's also a really good cat toy when you put it on the ground like that. And instead of doing it with a single string with just pointing at one spot, I pointed a tube, right? A 3D printer printed this by pointing the nozzle and tracing all of this out. But it did it in layers. It's the only difference between a 3D print and the actual vector function. Another picture of that same curve is on page 851. That's also the same knot. We're just looking at it from a different angle. That is also a 3-dimensional vector function. It's a circle, but instead of going out the z-axis, I went in another circle. Where am I going to see something like this? This is a solenoid coil. That's a starter engine. Put a magnet in the middle of this, you get an electromagnet. Put an iron bar in the middle of it, you get an electromagnet by passing electricity through it. Put a magnet in the middle, it generates electricity by moving the wire around it. That's how your starter works in your car. Spins the magnet, generates electricity on the wire. I could draw all of these in the graphing program on my MacBook. Grapher. 3D. Make sure we share that so you can see it in the video. Share. Now, if I want to graph this, I don't need z equals, I need r equals, right? But that was x of t, y of t, z of t. So over here, under the inspector, there's this little sigma with a down menu next to it. So I'm going to get rid of this equals z here. And I'm going to go over here and I'm going to say, hey, give me a 3D thing. It even says 3D parametric curve. X equals Y equals Z equals. Put an equal sign. Make another one. And now you can put in the functions in terms of t. So I'm going to go up here and change x. X is going to be cosine of t. Ooh, I'm in caps lock. That's not going to help. Cosine of t. Y is going to be sine of t. And z is going to be t. Then I need to tell it what t's to use. Comma. T equals 0 to 2 times pi. And I literally just typed the word pi and it replaced it with the symbol. There's my helix. If I look at the top, if I look down from the z-axis, I can see the circle. If I look from one side, I can see the cosine. If I look from the other, there's the cosine. If I look from the other side, there's the sine. But there it is spinning in 3D for me. If I have the parametric equations, I can draw this sucker. I am a crap artist. I very, very, very much am thankful for the computer. Okay. We said this was on a cylinder, right? I'm going to draw the cylinder. Actually, I'm going to rearrange this a little. Hang on a second. Let's point it out the x-axis. There. Now it's pointing out the x-axis. Yes? So if I add grapher, object, equation, new equation, boom. Now I can add something else, right? Let's add the cylinder. X equals y squared plus, I'm out of there, z squared. I need the plus between them. Ah. No. That's not a cylinder, that's a paraboloid. Why is that a paraboloid? Because I wrote it x equals. In order to be a cylinder, it has to be missing a variable. I can't have all three. There's the cylinder, and you can even see how the curve sits on the cylinder. Son of a... That's a lot better than a paper towel roll with a marker on it. Now, when I did this the other day, I drew a couple of different surfaces. So I could take something like a cylinder. Let me go back to this one. X squared plus y squared equals. There's my cylinder up and down, right? What if I said I also want to look at a plane? Y plus z equals 2. That plane cuts that cylinder, yes? What shape does it make when it cuts them? But if I cut this, well, I've actually drawn that on here as well. It's a little hard to see, but I cut this at an angle with this line, and it looks like an oval cutting through this way. Well, I could find the equation for that curve by doing a parametric description of it. So remember, we had x squared plus y squared equals 1. That was our cylinder. We also had y plus z equals 2. Well, another way to write that is to say z equals 2 minus y. Yes? So let me do parametric things. If I'm just looking at that x and y, I can think of the circle it makes, right? The circle it makes would best be given by x equals cosine of t and y equals sine of t. But now I'm going to take that circle, which as I've written it, is at a height of any z I want. Yes, that's what the cylinder is. It's any z. I'm going to say, no, 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 no. I want one particular z. And the z I want is this z. And so I'm going to say, oh, well, then let's let z equal 2 minus sine t. If you graph those three equations in our grapher, you should get a picture like this. A cylinder intersecting with a plane gives me an oval in three-dimensional space. Page 850. I've run out of time, but I want to throw one more thing at you before you leave. My absolutely most commonly used curve. R of t equals t squared, t cubed. That's called the twisted cubic because it looks like a cubic equation when you just look at x and y. Or when you look at it this way, it looks like a parabola. When you look at it this way, it looks like the square root of a cube. But it's really all three at once, depending on which way you look at it. This has the supports still in it. But here it is with just the axes, the cube itself, hanging in three-dimensional space, x and y and z. I printed a lot of these so that I could make them stand up. But that's the idea. I have this curve floating in 3D space. How do I find it? Well, I point at it. There are some pictures of the twisted cubic on page 852 and 853. A mass spec measures the deflection of a particle through a magnetic field, generates some sort of spin curve, finding that curve, tell me where the particle went, where did it hit my screen, tells me how heavy it was, the effect of the charge versus the mass based on the electric field. Again, useless, never going to see it anywhere. All of my instrumentation work is curves in 3D. Thank you all very much. I will see you all on Wednesday. And yes, Wednesday is a review day. And it is all the discussion for exam 1. The review sheet is posted. And I will see you all, and you are entitled to make an index card. I'll tell you more about that on Wednesday. See you then.